This presentation on domain rules will make a lot more sense. You'll be able to follow it a lot better if you have the handout, which I will put a PDF in the link to a PDF in the YouTube box. And it should look something like this. That'll help it make a lot more sense. I'd like to talk about finding domain in relationship to going on a blind date. So some of you may have been on a blind date before. And when you go on a blind date, your hope and expectation is that your date is going to be perfect. And then you meet the person, and as you're going through the date, you probably have some kind of a mental checklist. Oh, well, you know, he's not very considerate, or she's talks too much, or, you know, you go through a little checklist of things that help you evaluate the date. Well, it's the same thing with domain, because when you first meet a function, you're introduced to a function, you want to assume that its domain, all real numbers, negative infinity to positive infinity. And then you're going to go through a checklist to find out if that's really true. And that's what we're going to do right now, is go through this checklist. And it is important to go through this checklist in the order in which I am describing. So the mnemonic that I use is don't ride lions, dear. The don't stands for denominator. The ride stands for radical sign. The lions stands for logarithm. And the last dear stands for defined. We'll go through each of these individually, but these are the only things that we're going to enter your domain of your function. So let's start with the denominator. The question you have to ask first when you're looking at the function, does the expression have a denominator, and is there a variable in the denominator? Because if there is a variable in the denominator, any value of that variable, which makes the denominator equal to 0, has to be removed from the domain. So one example was this right here. I have x plus 6 divided by x minus 5. Well, I have a denominator, x minus 5, and it has a variable in it, x. So if I want to find out what can't be in the domain, I'm just going to go x minus 5 cannot be equal to 0. I add 5 to both sides, x cannot be equal to 5. No matter how complex your denominator is, and we'll look at some examples later on, what you need to do is set the denominator equal to 0, and then solve for x, and you'll find out what has to be excluded from the domain. So in this case, I would write my domain in interval notation. I'd say, well, I go all the way from negative infinity, and I go all the way to 5, but I don't include 5. That's what the parentheses means, don't include it. And then I'm going to unite that with the other part of the domain, which is starting at 5, again with the parentheses, so 5 is not included, and that's going to go all the way to infinity. Now, if you see something that looks like this, and I'm going to do a pretty simple example, but let's say x over 2 is my function. F of x is x over 2. Well, do I have a denominator? Yeah, I have a denominator, but there is no variable in the denominator. And I could really rewrite this as 1/2 x, so you can see that it's really like a constant times a variable. So you really need to worry about that. So let's see if I can just do one more example here. So let's say I had this function here. Well, I have a denominator, and the denominator has a variable in it. So I'm going to just take my denominator, x squared plus x minus 12, and say that cannot be equal to 0. So I can factor this into x plus 4 x minus 3, and I can see that cannot be equal to 0, so I can see that x cannot be equal to negative 4, and x cannot be equal to positive 3. Neither of those are acceptable, so those are both out of the domain. Now, whether they are whether they are vertical asymptotes or whether they are holes in the graph is a whole other story, which we're not going to get into right now. I'm just trying to help you understand domain. So if I was to write this, those are the only two numbers that are excluded from my domain. So I can go from negative infinity all the way to negative 4. I have to end at negative 4 with the parentheses. And then I'm going to unite. Remember that I can go from negative 4 to positive 3. Those are all good numbers. And I can unite that with 3 to infinity. So that would might be my domain using the denominator, the don't part of the don't ride lions deer. Let's look at the second part of the test. Is there a radical sign in the expression? And it has to be a radical with an even index. So just to get a little bit of a refresher course right here, this is a radical sign. It is not necessarily a square root. It's a square root when this is blank, but that's a radical sign. The little number that we put here is called the index, and what is under the radical sign is called the radicand. It's a good idea to understand these terms. So this is the radical sign, and this is the index. Now I'm just going to use a couple of simple examples here. The graph of the cube root of x looks like this. The domain of the cube root of x is negative infinity to positive infinity. There's no real restriction on a cube root. That is because it is an odd index. If I was to look at the graph of the square root of x, that looks like this. Here's the square root of x. Note there's an assumed 2 here, so that is an even number index. And the graph of that looks like this. It starts here at 0, and it goes like that. And that is because we cannot have any negative numbers underneath the radical sign. We can't take the square root of a negative number. So I look for a radical sign, and then I look to see, does it have an even index? If it has an even index, like my example right here does, I take the radicand, what's underneath the radical sign, so I have 2x minus 3, and I say that has to be greater than or equal to 0. Well, then I solve that. So I have 2x has to be greater than or equal to 3, adding 3 to both sides, divide by 2 on both sides. X has to be greater than or equal to 3/2. So my domain, it starts at 3/2, and 3/2 is included because it's greater than or equal to. That's why I use the bracket, and it goes all the way to infinity. So that's how I solve. If I have a radical sign, just take the radicand and set an inequality greater than or equal to 0, because we're not allowed to have any radicand that is less than 0, that is a negative number. The third test is whether there is a logarithm in the expression that we're trying to find the domain for. And is there a variable in the argument of the logarithm? And just to kind of get, again, our terminology straight, if I have, this is not related to this, but if I have f of x, the thing that's in the parentheses, the input value that's in the parentheses, is called the argument of the function, G-U-M-E-N-T. So logarithm is a function, and it always has some kind of an argument. And the thing about a logarithm is that the argument has to be greater than 0. Now, I don't want to mean that the logarithm has to be greater than 0, but the argument argument has to be greater than 0. So again, here's an expression. My argument is x plus 2. So I just set x plus 2, and I say that has to be greater than 0, not greater than or equal to, just greater than. Subtract 2 from both sides. X has to be greater than -2. And if I write that in interval notation, my farthest left side, my lowest value is -2, and it is not included, and it goes to infinity. So that's what I need for logarithms. The argument of a logarithm has to be greater than 0. Finally, I come to define. This is the deer part. Don't ride lions, deer is the last D. And sometimes you'll see a function that looks like this. It's a regular looking function, but there'll be a comma, and then they are defining the domain for which we want the values of this function. So this is saying, we want the values of this function between -5 and +4, not including -5, but including +4. So you might think that the domain for this function here is simply -5 to +4. Oh, +4 would be included because it's less than or equal to. So I'm going to use a bracket there. But that's why, one of the reasons why you have to do these steps in order, because if you did the very first step with this function here, you would see that x cannot be equal to 0. So that's why the actual domain of this function is -5 to 0, 0 not included, and then I'm uniting that with 0 to 4, which in the 4 is included. So I'm going to work through with you one of the more complicated problems. And I'm going to remember that I want to do don't ride lions, deer. So I'm going to start out with denominators. Do I have a denominator here? I do. My denominator, and I have to look at the entire denominator. I know it's a logarithm, and I'm going to get to that when I'll look at the inside here. But I have to make sure that log x minus 10 is not equal to 0. Now, a logarithm is an exponent. So this is really log base 10. And if I put this in exponential form, it'll say x minus 10 cannot equal 10 to the 0th power. So x minus 10 cannot equal 1. I'll add 10 to both sides. X cannot equal 11. So 11 is out of my domain from the denominator side. All right, so this is denominator. Well, let's look at the radical sign. Do I have a radical sign with an even index? I do. It's right here in my numerator. So I take the radicand, so I'm going to go radical signs. I'm going to take 3x minus 7, and I say that has to be greater than or equal to 0. So 3x has to be greater than or equal to positive 7. X has to be greater than or equal to 7/3. Okay, that's my radical restriction right there. Now I'm going to look at logarithms. So if I'm looking at logarithms, let's do it like this. Log. My argument, which is x minus 10, has to be greater than 0. So x has to be greater than 10. And then I look to see, is it defined anywhere? And I don't see that it's defined anywhere. So the way that I find it easiest to then really look at the domain is to use a trusty number line. So here is a number line. And looking at values here, I'm going to start at 0, and here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So here's 5, here's 10, and here's 15. So my first thing over here in blue is saying, so remember, I'm first imagining that it's all real numbers, but my first thing is saying, nope, it can't be 11. So at 11, I know I'm going to have an open circle. And then in the red, it says it's got to be greater than 7/3. 7/3 is a little bit bigger than 2. So greater than or equal to 7/3. So I'll put a little dot here at 7/3, and I'll say it can be anything like this, just as far as a radical sign. I'll combine them all in just a minute. So let's call this 7/3. And then my last one says x has to be greater than 10. So I come over here to 10, and I have an open circle at 10, and it goes all the way that way. Now, if any one of these restrictions is violated, that is out of the domain. So even though it looks to me like, using the radical definition, that 5 would be okay, 5 looks like it should be okay, but 5 violates the green restriction and the blue restriction. Well, that doesn't really restrict the blue restriction. The blue restriction would actually look like this. The denominator one would actually go all the way to negative infinity and all the way to positive infinity. So again, 5 looks like it might be good from the red standpoint, and it's okay from the blue standpoint, but it doesn't pass the test for the green. And I cannot violate any one of these. So I can see just kind of like think about what a line would look like if I was to draw it up from the x-axis. I have to cross all 3 lines. So here, between 10 and 11, I am crossing both lines. I have all 3 lines. I have the blue is okay, the red's okay, and the green is okay. So I know that I have, not including 10 because it's an open circle, I can go from 10 to 11, and I'm in pretty good shape. But at 11, I have a hole there, and I can't do it. Once I get past 11, I'm covering the blue, the red, and the green. So I'm going to unite that with 11 to infinity. So that is how I find the domain of a function. I hope it was helpful.